Good afternoon. We'll start now. Let others join in between. Good afternoon, all the distinguished fellows, faculty members, participants, and esteemed Professor Damodar Acharya sir, who is away, who is having some connection issue, so is not present at the headquarters. Director IMMT, Dr. Ramanuj Narayana, Director of the IIT Bhubaneswar, Professor Sripat Mamalkar, Professor Debendra Kumar Das, who is the speaker today, he is with us. Professor Renu Sharma, the coordinator and additional dean of Students Welfare, Faculty of Engineering Technology, and all our guests today, and all the participants, fellows, distinguished fellows. Today is the 30th lecture of the Distinguished Lecture Series, organized jointly by INE Bhubaneswar Chapter, Shiksha Anusandhan University, CSR, IMMT Bhubaneswar, IIT Bhubaneswar, and IEEE Bhubaneswar subsection. This is the 30th one, and the speaker is very eminent personality, Debendra Kumar. He is currently Professor Emeritus in Department of Mechanical Engineering, University of Alaska, Fairbanks, USA. It's my pleasure to introduce Professor Debendra Kumar Das to the entire audience. Professor Das, he had a beginning from this Odisha, and he had his BSc Engineering with honors in Mechanical Engineering from REC Raurkela that time, currently NIT Raurkela, in the year 1972 with first class honors, and also was a gold medalist in Sambalpur University among the two institutes, REC Raurkela, Dhiren and UC Burla, now NIT Raurkela and VSSUT. And thereafter he, I think, pursued his master's from Brown University in MS in Mechanical Engineering, Rhode Island in 74, and PhD in Mechanical Engineering from University of Rhode Island, 1983. He was also the past Mechanical Engineering Chair of Mechanical Engineering, University of Alaska, Fairbanks, and he joined University of Alaska in 1984 and was up to 2018, joined as assistant professor and was promoted subsequently to associate and full professor in the Department of Mechanical Engineering and served the department till 2018. And also he served in industry and government as design engineer, Tower Iron Works, Massachusetts, Basic Inflow, Rhode Island, research engineer, Naval Surface Weapons Center, Virginia. And also he has been awarded with a lot of awards and honors. He has been included in the Who is Who among American teachers in 1998, elected as Fellow of American Society of Mechanical Engineers in 2004, and Dr. Carol faced Outstanding Advisor Award in 2003-4 and 2005-6 at the University of Alaska. ASME Student Section Advisor Award among all districts of ASME International 2006. USA Distinguished Service Award from National Alliance on Mental Illness 2007 USA. Past President of NAMI Fairbanks Affiliate USA. Dedicated Service Award from ASME International 2007. Past Chairperson Northern Alaska ASME International Subsection USA. And also Disability Distinguished Teaching Award, University of Alaska Fairbanks in 2012. Distinguished Alumnus Award by Zone Alma Mater NIT Raurkela in 2007. Today's Professor Das will deliver his lecture and experimental evaluation of nanofluids in building heating coils, followed by computational analysis of nanofluids for cooling in micromechanical heat exchangers. Professor Das has a fairly rich experience and long experience in this area. It's a pleasure to have Professor Das with us. Welcome, sir, to this distinguished lecture series. Now I request Professor Das to deliver his lecture.
Screen. Thank you.
Full screen.
Thank you, Dr. Nanda, for that beautiful introduction. Distinguished audience of the 30th INA lecture series, I feel truly privileged to be here today and share some of the research findings that we have obtained on nanotechnology. I have been working in this area for about 25 years, and the work I'm going to present is the work of my former doctoral student, Dr. Royce Franberg. My talk is divided into two parts. The first part is an experimental evaluation, and the second part is a theoretical evaluation. Currently, I serve as a professor emeritus at University of Alaska, Fairbanks, USA. The outline of my presentation will be introducing how the microtechnology began in 1960s and it progressed to nano scale over the years. Then I'll show some of the samples, some real world objects which appear in nature, and they're of micro and nano scale sizes. Then we'll talk about the heating coil, which is predominantly used in cold regions of the world. Since I come from Alaska, there is a lot of importance in designing very efficient heating coils to heat buildings. We heat our buildings for about 7 months of the year. Many of the northern provinces, Canada, and circumpolar nations like Scandinavian countries, they also focus heavily on the efficiency of hydronic heating coils. So it has been our goal to develop a very efficient heat transfer fluid, which will make our heating systems quite efficient. First, we'll show you the experimental setup, then some specification of the air coils, and then we'll compare the performance of basic fluid which we are using nowadays, because nano fluid is not used commercially yet. It's not commercially adopted yet, but it's our ambition or aspiration that we use it.
Switch off here and switch off. No. So now we'll not switch off there. We'll switch off from here only. We'll switch off only the set-top box from there. TV அங்கே இருக்கலாம். TV is now on the left. So அணைக்கணும்னா right hand side அணைக்கணும், இங்கே அணைக்கணும் இதை. That's what I want to try.
Then, okay. Yes. So maybe more check. I have completed. Then the second part of the talk will be on computational fluid dynamics, theoretical analysis that will prove that nanofluids is indeed going to be an efficient fluid. Then we'll conclude with some of our research findings, and I'll finish the talk with acknowledgements. As I mentioned, this nanotechnology began with initially microtechnology in the year 1000. That's okay. It's okay. So, back in 1959, Professor Richard Feynman, who was a Nobel laureate receiving Nobel Prize in 1965, a physics professor at Caltech, he gave a prophetic talk. His talk was, there is plenty of room at the bottom. What he meant by that is that when you go to very small scale, there is plenty of room to do research and development and improve our engineering system. So he challenged the scientists at that time and engineers to build an electric motor which is no larger than 1 by 64-inch cube. And he announced a price of $1,000 in 1959. To his surprise, William McClellan, who was an electrical engineering PhD student at Stanford, completed this motor in 4 months, and he used tweezers and a microscope. The motor had 15 parts. It weighed 250 microgram, rotated at 2000 RPM. It's still on display at Caltech, but it no longer spins. So the birth of microtechnology began with this micro machine, a small scale motor. We see microscale materials and nanoscale materials in nature. So we begin with the left side of the slide. Within the human eye range, we have a marble which is about 1 centimeter diameter, 10 to the power minus 2 meter. The pinhead is about a millimeter, 10 to the power minus 3 meter. Mosquito is of the same scale, about a millimeter. Then, smaller than that is in the microscopic range. Red blood cells, they are about 10 to the power minus 5 meter, and the bacteria are 10 to the power minus 6 meters. These could be seen in the microscope. When we go further smaller, we have virus occurring in nature. They are 10 to the power minus 7 meter, or about 100 nanometers. These are all in nanometer range. We can't see them with microscope, but we can see them in electron microscope range. They are in that range. Then DNA strands are of the order of same 10 to the power minus 8 meter, and carbon nanotubes are about 10 nanometer. And smaller than that are in the atomic range or angstroms. The nanoparticles that we are doing experiment on now are less than 100 nanometer.
54 and 65 or something like that.
Yes. The aluminum oxide on the right hand side, you see an electron microscope figure.
Yeah.
We have nanoparticles there about 30, 40 nanometers to about 60 to 70 nanometers. The nanofluids that we are using are of the order of about less than 100 nanometer. It is being used presently in limited way. It's being used in catalytic converters, where platinum nanopowders are being used to increase the reactive capacity in absorbing the pollutants. In rubber tire, we are using carbon black nanoparticles to improve the wear resistance on the surface. We have sunblock lotion, titanium oxide and zinc oxide nanoparticles are being used in the lotion as sunblock lotion, and it's also being used in dentistry as powders to make very strong, improved false teeth. On the bottom diagram, we see the carbon balls, agglomeration of the carbon atoms. These are called Bucky balls, first discovered by a professor at Rice University in Houston. Next to it is carbon nanotube, about 10 nanometer. They are of the same size as human DNA, and also small chunks of protein fall under the same category. We are using silver nanoparticles in pharmaceutical industry. The virus are of size 100 nanometer, and then the bacteria, they are slightly larger in microscale. Red blood cells are in microscale, and when we come to the human hair, it's about 1 millimeter range. So many of these micro and nanoscale particles do occur in nature. So in the talk, I'll begin with the application of nanoparticles and nanofluids and the active research which have been accomplished since early 2000. These nanofluids have been studied for solar thermal application, automotive radiator cooling, liquid to liquid heat exchanger, micro and nanoscale heat exchanger for cooling, both cooling and heating. In heating, we heat the buildings. In cooling, we cool the radiator, we cool the micro heat exchanger, which are cooling electronic equipments and electronic chips. Our work goes back to early 2000. In 2009, we first published our paper, Analysis of Liquid to Heat Exchange in Fin Tube Air Coil. And at that time, the theoretical evaluation predicted that nanofluids would yield a substantial boost in the performance. And we published that in 2009 with my student, Dr. Roy Strand. At that time, these were all theoretical work, and we were using in the theoretical analysis equations of viscosity, thermal conductivity, specific heat, which are of pure nanoliquid, and we always assume that that high property will always continue. And with that hope, we wanted to do experiment. Once we are convinced by our theory, we wanted to do experiment in air coil to see that whether what we predicted by theory is going to hold true in experiment, in real world. But this result, which I'm going to show you, experimental result, proved otherwise. We found that it is very difficult in the real world to maintain very pure, high-level quality of nano. The thermal quality of nanofluid degraded very quickly, and we have a lot of pitfalls. We have to overcome those pitfalls in order to make this superior quality of nanofluid be functional and be used in the future. So our study objective was to do experiment and prove it. So we began testing pure liquid that we are using nowadays. In cold regions, we use 60% ethylene glycol, 60% propylene glycol in heating oil because temperatures goes below 0 degrees Celsius, cold region, water will freeze. In warm climate, in Texas or Oklahoma, we use water in heating. But in northern climate, Minnesota, Massachusetts, Vermont, Alaska, all over Canada, we use this ethylene glycol. So we circulated pure ethylene glycol and then also 1% aluminum oxide impregnated aluminum nanofluid. And we wanted to prove that nanofluid should prove better. But as the experimental results will show, we had a great disappointment. Initially, to qualify our test bed or test setup, we did some baseline performance. We circulated water and glycol, and we proved that our experiment is proving that the theoretical equations for heat transfer coefficient, Nusselt number, all these and heat rate should match because theoretical equations have been all established 40, 50, 100 years ago, and our test bed must first replicate the pure liquid. Then once we prove that, then we'll go and introduce nanoliquid and evaluate how it is performing. We measure temperature rise of nanoliquid and air because it's going to heat the room air. We'll calculate, we'll determine, measure pressure loss, and the pressure loss will give us what is going to be the pumping power for different liquid flow and different Reynolds number of flow. We'll calculate liquid side Reynolds number, air side Reynolds number, Newsort number, heat transfer coefficient, friction factor, and exergy. Exergy is a measure of production of entropy, which is a measure of second law of thermodynamics. And it shows that following the second law of thermodynamics, whether the system is operating efficiently or not. Then we'll compare the performance of nanofluids with the base fluid. Base fluids are pure liquid, which we're using right now. Then we'll draw some conclusions. The test conditions were that we formulated or prepared nanofluids in our mechanical engineering materials lab at University of Alaska. We don't prepare this nanofluid suspension because we don't qualify for all the security and safety. So we purchase them from Alpha, which is a company, and it gives a concentrated solution of 50% colloid and dispersion, all below 100 nanometer. And this company is in Massachusetts. It provides nanofluids to different kinds, aluminum oxide, copper oxide, silicon dioxide, oxide, titanium oxide. It provides to many labs, research lab and university. Then we bring that in and we mix that with lab-grade ethylene glycol that we use in oils nowadays. We mix that with deionized water, glycol water, and then we mix this concentrated nanofluid. Then we make very dilute 1%, 2%, 3% volumetric concentration nanofluid. We selected maximum entering liquid temperature of 327 Kelvin and entering air temperature 298 Kelvin. These are the realistic temperature at which our manufacturers of heating coil recommend that this is what we supply to the cold region. Then we vary the liquid flow rate and circulate the liquid at various Reynolds number, and then we evaluate how much heat it is transferring to air, what kind of heat transfer coefficient is creating in the coil. And our test facility was at Cold Climate Housing Research Center Lab, CCHRC Lab, which is located in Fairbanks, Alaska. This is the schematic diagram of a hydronic heating coil. It is installed in the duct. Air enters from the left side, cooler air enters from the left side, glides over the U-tube coil, which is made out of copper, and these copper tubes have large number of fins. The space between these fins are only 2.5 millimeter. Large number of fins. Through these fins, we transfer the heat from the hot liquid, which is going through the copper tubes, to the air. Then the warm air comes out on the right-hand side of the coil, air coil, and that air is injected into the room, and it keeps the room very warm and comfortable. This is a photograph of the air system and the liquid system. On the top, you see the air handling system. From the right-hand side, we introduce the cooler air, and there is a venturi. That long tube is a venturi, which gives us the volumetric flow rate of the air, how much volume flow we are bringing in. Then in the middle of that duct, we have that air coil, the copper coil. The copper coil is receiving liquid from the series of piping on the back, on the wall. On the wall, you see a series of piping. That series of piping is circulating either pure hot liquid or pure hot nanoliquid into the coil. And on the left side of the duct, looking rectangular, inside that there is a induced draft fan, which is sucking in the air, and as the air glides over the heating coil, it gets warm and comes out. We measure entering air temperature, entering air pressure, pressure loss, so that we can calculate the air side pumping power. We also measure the temperature of the liquid, volumetric flow of the liquid. Those are all through the liquid meters mounted on the wall. So the liquid side piping, you see there is a lot of piping down on this bottom photo, and the red pump, that's a circulating pump that circulates the liquid in the heating coil. And on the right side, we have a micro heat exchanger, which is bringing in hot fluid, heating the nanofluid or pure liquid, and then it is discharging into the coil. And in the coil, nanoliquid gives the heat, gets cooler, goes back to the liquid loop, gets heated again with hot fluid, and the process continues. In this process, nanoliquid gives the heat to air. This is a schematic diagram of the experimental arrangement. On the bottom part of the diagram, we have the air system. On the top part of the diagram, we have the liquid system. On the top left, we have the heat exchanger, which is providing the heat to the nanoliquid. And all the series of lines is connected on the left bottom part to a data logger. And this data logger is constantly monitoring, every minute it's monitoring incoming temperature, outgoing temperature, volumetric flow rate, liquid, air, and also the pressure loss and various thermodynamic parameters that we'll need to evaluate heat rate, heat transfer coefficient, pumping power, and all these things as a function of different liquid flow rate. We use LabVIEW software, and LabVIEW software uses to control the incoming fluid volume, incoming liquid rate, also incoming air temperature, controls that incoming pressure, changes all these, and every minute it records temperature, pressure, and other flow rate, and it records in the data logger. And at the end of the experiment, sometimes you run the experiment for many days, and at the end of the experiment, we collect all the data. We set one Reynolds number with particular volumetric flow rate, and we take hundreds of measurements. Then we change the Reynolds number by increasing the flow rate, and we take similar measurements. All these are recorded finally from the data, and we download this data, and then we analyze and plot these results to find what the results are showing us. Every instrument you use have inherent error because none of the instruments are perfect. So we have liquid flow meter omega makes it, and omega tells that this liquid flow meter has this error of plus or minus 1%. We have liquid thermistors which measures the temperature. Those thermistors have inherent error of plus or minus 0.1 degrees Celsius. We have differential pressure transducer. It has an error of 0.25% full scale error in the pressure, because all these are very accurately measured by their manufacturer, and the manufacturers give us these numbers. Once we get these numbers, then we take the square root of some of these errors, and then we predict that the experimental results we are presenting has this error. When we add square root of some of these errors of all different instruments we have, we get maybe 2%, 3%, 4% error. So we say that's our uncertainty analysis. The results we are presenting have uncertainty of 3 or 4 or 5%. And this is always inherent in any experimental observation. So here are some of the results that we obtained. On the x-axis, we have the volumetric flow rate of liquid pure liquid. And here we are testing water first to verify our test bed. We want to make sure that what our test bed is giving from experiment matches with old established theory for water, which is well explored 50, 60, 80 years ago. We have equations for water, we have equations for pure liquid, but there is no equation yet for nanoliquid. So, and then we have the results for air. On the y-axis, we have the heat rate. If everything will be ideal in this world, then with a different volumetric flow rate, the red dots and the blue dots should fall over each other, which will show that whatever heat the liquid is carrying, it is given to the air. But we have inherent losses always. Also, we have inherent irreversibility in the process. So always there is bound to be some difference. But this agreeability is fairly close, and these agreeabilities within the margin of established experiment. So experimentalists, they say that the test bed is working reasonably well because it is showing that the energy balance between the air, the heated medium, and the medium which is giving heat are more or less same over a broad range of volumetric flow. Then another criteria we tested to prove that our test bed is good, and that criteria is that we used pure 60% easy, which is ethylene glycol, which is used nowadays, and we measured the Nusselt number. Nusselt number was calculated from measured properties, and on the x-axis we have the liquid side Reynolds number, which is this nanoliquid and pure liquid circulating in the coil. And as you see, the red globules, those red dots, those are actually collection of hundreds of points. Every minute we are measuring this and calculating. So those are actually collection of 100 points. And say at a Reynolds number of 5,000, if you go up on the reds, you see whole globule. So that may be about 70, 80, or 100 points, and they are all consistent, one falling on each other. We found that the red one, which is for ethylene glycol, Nusselt number calculated, matches very well with Petukov relation. Petukov relation is a very, thank you. Petukov relation is a very well-known theoretical relation known for long time, and our experimental data are falling right through the Petukov relation. So this gave us the idea that whenever we evaluate a fluid or best fluid oil, pure liquid will always compare it with Petukov relation, because Petukov relation is well known, well proven, and our experiment is replicating that. Below that, on the blue line, we see that that's the nanoliquid experimental point, and that is exactly matching with another relation, which is Dittus-Boulter relation. So we decided that henceforward, when we will do any experiment with nanoliquid, we will verify that with Dittus-Boulter equation, because nanoliquids are following very faithfully Dittus-Boulter equation. So these results gave us the faith that the experimental test bed we have done is reasonably good. It's reasonably accurate. Then we calculated the heat transfer coefficient. On the y-axis, we have heat transfer coefficient, and on the x-axis, Reynolds number. And this is the this first time we were disappointed, because we were thinking that the red dots, which are for 60% easy pure liquid, will be giving a little less H, little less conductive coefficient, because all our theoretical analysis says that nanoliquid will be higher. It turned out from our experiment that the blue dots, which are for the 1% aluminum nanoliquid, is giving slightly less than the pure liquid. So we immediately realized that we are not able to translate what we are seeing in theory to real world because there is some flaw in our nanoliquid system. And we began to think that why it is happening and what is the problem. We also calculated the heat rate, measured the heat rate, how much heat is going into the liquid, from the liquid to air, and we found the similar kind of story that the aluminum is just barely better than the pure liquid. Just few points we found slightly maybe within 1%. We are expecting 3%, 4%, 5%. Theory has given us those results, but we found that they are just barely better in absorbing the heat. So what is the problem? As we began to think, we examined the nanoliquid from our loop, and we found that those nanoliquid don't exhibit as good the property as it had when we first introduced, when it was very fresh. It degraded very quickly. There was agglomeration and other things which I'll summarize later on. The heat rate versus hydraulic power. This is how much pumping power we are investing in the liquid loop to our liquid pump, and how much heat we are getting as our benefit. And we found again that with pure liquid, with smaller amount of power, we could give more heat. If we take constant hydraulic power 0.1 watt, we find that the pure liquid is given higher value, whereas the blue one will fall somewhere here. That means at the same hydraulic power expenditure, the pure liquid is better, nanoliquid is inferior because of higher viscosity, and also degrades much more. A slight higher viscosity we had calculated theoretically, but that was not that big to overcome the improvement in heat transfer. However, the nanofluid was degrading very quickly. So, from this initial set of experiment, it opened our eyes that 1.1% aluminum oxide exhibits slightly lower heat transfer coefficient than the 60% Eg. This is the only plus part, slightly higher heat transfer coefficient. Nanofluid Nusselt number agree with Dietz-Bolte. So we'll always use Dietz-Bolte equation. Any further experimental work taking those experimental value will always check it with the Dietz-Bolte equation. 60% Eg, which is pure, Nusselt number prediction agrees very well with Pettigrew correlation. So by and large, the experimental setup is replicating what the old theory had predicted. At 3000 Reynolds number, we found a heat rate of nanofluid coil was 3.2% higher than the 60% Eg fluid coil. These are by no means very promising results because it disappointed us. We were full of promise when we were doing theoretical calculation. When we did the experiment, we found that we are not able to maintain the purity of nanofluid in our system, which is degrading very quickly. We have to do much more research to really develop a very stable form of nanofluid. Challenges. After thinking a lot, analyzing our experimental setup, we found other problems also. The system contains a lot of air bubbles because the liquid pipeline which is supplying the liquid is full of turns, bends, valves, and they were trapping air. When the air is there, we were getting very poor results. So we couldn't ensure full charge. Liquid is completely filling, all the pipe was not happening. There are some voids here and there. So the liquid line must be designed with utmost care to avoid that. Cleaning the test fluid out of the system was a problem when we used 1% aluminum oxide. After we finished the experiment, we had to clean and again test pure water or pure glycol. When we cleaned those, we found that in pockets, there was still some old aluminum oxide fluid still sitting. So the cleaning the test fluid loop was a huge challenge. Nanofluid stability was a big problem. We found that once we used this spent nanofluid, it had degraded very quickly. The particles have agglomerated. The surfactant that was used to keep the particles separate, they have also degraded. The pH value changed. So we have not yet developed a very high quality nanofluid. Theoretically, it is predicting excellent thermal conductivity, excellent specific heat, excellent viscosity, but once it becomes agglomerated, it turns into microfluid, almost like microfluid. 100 nanometer particle, we measured the particle due to sedimentation. The heat transfer wasn't well. From the sediments, we measured some particle size. They were much larger because the particles have agglomerated. And once particles agglomerate, nanofluid loses its capability. And maintaining a steady entering air side condition or entering temperature or changing because where our experimental setup was, there were some doors nearby, and often people while accessing those doors will open. And in cold climate in Alaska, once you open the door, cold air comes in, which is at maybe 4 degrees Celsius or something, and immediately the air side temperature fluctuated. We wanted to do experiment at a very controlled, constant air side temperature so that we can predict the performance of air coil very well. So with all this knowledge, we wanted to change our experimental system and we wanted to improve it and we wanted to do experiment and have some better quality, try some better quality nanofluids and simplify the liquid loop so that we'll approach a better real world system. Our initial real world system was really not good, it was crude, so we started refining. And that's the way it goes. I think this system will be refined and refined and refined. And someday, several years from now, we'll have the loop, which will be perfect. We'll have nanofluid stability, and what the theory is predicting, we will achieve that. But now, we are not achieving. So this time, we used 3 concentration nanofluid, 1%, 2%, 3% aluminum oxide in the coil. We measured temperature rise and pressure loss exactly same in the old experimental setup, but now the experimental setup is in a new place, calculated Reynolds number, Nusselt number, heat transfer coefficient, friction factor, and available energy or creation of entropy and loss of second law efficiency compared to performance of nanofluid and base fluid, and again, derive conclusion. So what modifications we did? We relocated our equipment to Golden Heart Utility Water Treatment Plant. This is a very big plant, very controlled environment, big room where air temperature doesn't fluctuate, it's isolated, controlled. There are huge volume of water to maintain thermal stability in the test area. We installed a new heat source so that we can heat our nanofluid to higher temperatures so that we can broaden the applicability of our experimental data. We reduce the liquid volume so that we have less entrapment and less collection at corners, bends, valves. Installed improved air venting apparatus, put an air vent on the top so the air bubble we can remove, and tested at higher entering liquid temperature. Initially, we used to do at 350 K, 327 K. We increased to 350 K because the manufacturer said that that will be covering a broader range and broader number of clients. And we tested multiple concentration nanofluids, 1 to 3%. And we used the liquid, pure liquid with these nanoparticles, which is commercial grade ethylene glycol, which is used nowadays. and it has some corrosion inhibitors so that it doesn't corrode the heat exchanger pipe section. So this is our new setup. This is our air section on the left side. The inlet air comes in, it's very controlled environment. We have the Venturi measures all the air properties, volumetric flow rate, and we have put some insulation in the middle which looks through that plastic. Under that we have the liquid coil so that we minimize the heat loss. We try to balance the energy balance, liquid and air side by minimizing the heat loss. There will always be some heat loss we'll try to minimize so that the liquid heat rate that gives out should be close enough to air heat rate that air receives. On the right hand side is our blower, and the air is released into the room. This is our new liquid side also on the wall, and on the top we have an air vent that allowed all the air bubbles to escape from the top. In the center we have the red circulating pump, and on the bottom we have the omega fluid liquid meter. This is the pump, and then we have a heat exchanger here, and this heat exchanger gets much hotter liquid to heat the nanofluid in those loops. And then we have introduced some control valves so that we can control the inlet temperature to the coil to various temperature, realistic real world temperature, and get the performance of the coil. So this is again the schematic diagram, and this gives a whole list of measuring instruments that we have installed. This is our data acquisition system, collecting data, pressure, temperature, volumetric flow rate, and various thermodynamic parameters, and it collecting and storing them every minute. And this is a big high temperature thermal system which gives heat to this heat exchanger. From this heat exchanger, we give to the nanoliquid, and nanoliquid is circulated right here. Nanoliquid is fed into the coil right here. And we have thermistors and all various devices which is constantly monitoring the temperature. So with this new setup, we also did the same thing. Reynolds number on the x-axis, heat rate on the y-axis, and you can see it is the heat absorbed by the air, which is shown by the rectangles, and heat given by the liquid coil is shown by the diamonds. And you can see that they are fairly close. They are never same. In ideal world, they should be same, but in experiment, they are all going to be different, and the kind of difference is acceptable to the experimentalist. So it shows that reasonable energy balance between water and air we are finding. Then we also tested our test bed using pure liquid. For pure liquid, we have Petrov relation does a wonderful job, and the Petrov relation is shown by this line. And pure liquid, these are our experimental data. And within the experimental uncertainty, you can see that for different Reynolds number, we are matching very closely what the famous Petrov equation says and what we are measuring as the heat transfer coefficient. So these are kind of verification of the test bed. And once the test bed is verified, we apply it to nanofluids. So here we have volumetric flow rate, which represent different liquid Reynolds number. On the y-axis, we have heat transfer coefficient. Inside heat transfer coefficient, inside copper tube through which nanoliquids are going. So the circles, the open circles and dark circles, those represent pure liquid. And then the orange is 1% aluminum, triangle is 2% aluminum, and rectangle is 3% aluminum. And this immediately opened our eyes that what we are calculating theoretically, and not us, hundreds of publications have come on the success of nanoliquids, but very few people have done experiments. And we opened the eyes that what we see in theory is not happening in real world. We are way behind in applying this nanoliquid, because the higher the concentration, we are finding that the lower is the heat transfer coefficient. The pure liquid, which we are using now, is still better because we haven't perfected the nanoliquid. We did the same thing with the Nusselt number, volumetric flow rate on the x-axis, and same story. These are 3% aluminum oxide gives the lowest Nusselt number, whereas the pure liquid is giving much higher Nusselt number. So there is definitely a lot of things wrong in practically using nanoliquids. And heat rate, same story, the amount of heat rate in to air in kilowatt, same story. For a fixed volumetric flow rate, let's say 1 liter per second, we see that the concentrated nanofluid is giving lower heat rate, pure liquid is giving higher heat rate. So we haven't yet reached the dream that we had thought of. Same thing with hydraulic power also. Nanoliquids always use more hydraulic power nanoliquids because they are concentrated, they have particles, they increase viscosity. So they always use higher hydraulic power, higher pumping power, we knew it. And the pure liquid they use with the same hydraulic power, pure liquid can give much better heat transfer coefficient. And also for the same heat transfer rate, we find a very small amount of pumping power gives that number. Same, very small, less than 0.5 here, gives high heat rate, whereas this gives are the same, much lower heat rate. So experimentally, nanofluids are proving to be inferior. Pressure loss, same story. For pure liquid, pressure loss is low for the constant volumetric flow rate, and the concentrated nanofluid is little high. And this is second law of efficiency. The initial energy balance comes from first law of thermodynamics, and exergy change or change in available energy. Exergy is a measure of how much entropy we are producing. If we are producing more entropy, then the system has more irreversibility. Nanoliquids, we found, is producing more entropy, as a result of which the available energy is diminishing. Why is it producing more entropy? This entropy generation, as the air glides over the coil, the entropy changes both on the air side, also entropy generation changes on the liquid side. Liquid is going through the tube, comes out at high temperature, goes out at a little bit higher temperature, and higher the entropy generation, higher is the exergy. And these are the equations. They are functions of mass flow rate of hot fluid and the specific heat of hot fluid, mass flow rate of cold fluid, specific heat of cold fluid, and incoming and outgoing temperatures of hot fluid and cold fluid. And when we measure the entropy change, which will give a measure of the second law efficiency of the new system, we found that again, the available energy is much more because it is not generating as much entropy. The function is not as much chaotic or as much irreversible compared to concentrated nanofluid. Why? Because these nanofluids is agglomerated. We haven't yet developed very clean nanofluid. Once it agglomerates, the particles are very big and they create high viscous dissipation. And this entropy generation is a function of high viscous heat generation due to fluid friction. As fluid friction increases, we know when friction increases, the process, thermodynamic process, becomes more irreversible. And so the second efficiency is also diminishing because we are not able to maintain the stability of nanofluids. And it's same kind of observation we found in the heat rate, that the exergy change is much more better. The available energy we can get is much more better, much more from the pure liquid. So what were the conclusions from this improved test bed? To our utter disappointment and sadness, we found nanofluids did not perform as well expected based on previous analysis. Previous papers we had published promising very rosy picture, and we are disappointed that in experiment we are not able to replicate that. So now the engineer goes back home trying how I am going to improve my experiment system so that I'll keep improving this so that my theoretical aspiration will be fulfilled. 2%, 2% aluminum oxide performs significantly worse than the pure liquid, which is best. 1% aluminum oxide required 100% more pumping power because increase of viscosity due to particle agglomeration. Nanofluids do not exhibit thermodynamically superior performance from the exergy analysis. We found the available energy associated with heat transfer from pure liquid is better than nanoliquid. So these were some of the disappointments. So upon analyzing our data, we found these are the challenges. Ensuring stability over time, especially at higher concentration, is not possible. We are not able to achieve that. Over a few days of running continuously, particular agglomerating, sometimes we stop the circulation because we don't need the heat. So we stop the circulation, and then at that time, the agglomeration is even more because fluid is not circulating. Particle agglomerator immediately settle down. Loss of enhanced properties. When we take those used nanofluid and measure the thermal conductivity, it is not as good as the fresh fluid which we had charged. And we found that nanofluids we are preparing now are highly sensitive to pH. When the pH degrades, changes, it reduces the thermal conductivity because pH is a function of a property called zeta potential. Chemists study those, and those zeta potential decreases and it attracts particles. Particles quality breaks down, and there are other factors which causes agglomeration and sedimentation. And viscosity becomes more because we are now circulating much bigger particles, and we need more fluid power to keep them circulated. So the pumping power also increases. So that was the learning process, and now we'll start improving. The experimental setup will keep improving. Now we'll focus on generating more stable nanoliquid. So that's the end of our experimental part. This is the beginning of, or this part is our computational part, theoretical part. Being very doubt-driven, we said that let us do some high-level computational fluid dynamic modeling just to convince us that the theory at least predicts that these nanofluids will do well. So we applied it computationally to microchannel, and these are some of these high power computer coolers, and these are the chips, computer chips, and they are cooled by this liquid. They are cooling. Now they are using pure liquid, inlet line, outlet line, and there are microchannel heat exchangers under these electronic chips and also electronic parts. And these are now being used with pure liquids, but nobody has used nano liquid yet until we develop the best quality nano liquid. So we developed a conjugate heat transfer fluid dynamic model of microchannel heat exchangers, and we wanted to compute their performance for pure liquids 60% Eg, and then nano liquids, copper oxide, aluminum oxide, silicon dioxide. modeling is very easy because we will put pure equations for their properties into our model. Different equation for thermal conductivity of copper oxide, another equation of aluminum oxide, another equation for silicon dioxide. Model doesn't realize that after running for a day or 2 or 5 days or a week, the same equations are not working anymore. But model always assumes that the properties are very good. So the model is based on that assumption. Then we'll find the thermal resistance value, and we'll find that if thermal resistance is lower, then we'll say that the heat transfer coefficient is higher. Inside heat transfer coefficient is one heat flux. These heat flux are coming from the high temperature, high power chips were running. Then we calculate the base temperature on which the chips are mounted, and once the base temperature is lower, we know that it's cooling a little bit better. And we calculate the pressure loss and how much pumping power we are investing for pure liquid versus nanoliquid. We used ANSYS Fluent version 19 three-dimensional modeling. It uses a mesh generation of its own. This is a very well-known program that everywhere, both industry and many universities, they are using. It uses very well-proven age-old theory, simple pressure velocity coupling scheme, very well-known, well-proven scheme, and it uses least square scale-based gradients. These are the options we choose while running the software. We choose second order accuracy for pressure, second order point scheme for momentum and energy equation solution, and all our flow are laminar flow because the channels are only micron size. So when you calculate the Reynolds number, since the hydraulic diameter is small, laminar flow, the number comes all below 1000. It's like from 50, 100, that's the number of Reynolds number. We selected 438,000 elements after making several runs. And then we validate our model by comparing the results previously published by Kandlikar, who is an authority in microchannel heat exchangers. So this is our geometry. Here we have the heat chips, and they give constant heat flux. And this is the heat exchanger. On the top, we have an insulated plate, and these are micro scale channel, micrometer size channels. And we do the theoretical calculation. And these dark lines are the liquid lines, then in between them, solid walls. Just like you see right here, these solid walls are usually called fin. So this behaves like a fin heat exchanger. So the liquid flows in, goes in here, and comes out at the exit here, collects the heat from the bottom, heat flux coming in for all the chips which are mounted on this base, and the chips get cooled because the heat is constantly being removed by this liquid. And this is another geometry of that. So we have here modeled one of those channels, half of the solid wall will be in and half of the liquid flow region. Here will be nanofluid region. This is the solid wall, hence it is called conjugate heat transfer. Here we will have the conduction analysis. Here we have the convection analysis. And we assume here that each channel is similar. So if we analyze one channel, then the results predicted by one channel will be similar to all these channels on the side. And the width right here is 45 micron, which is our right here width of the flow channel. So these are all micro channel heat exchanger. 90 micron is full. We have taken just a half because of the symmetry. And then the solid wall here is about 25 micron. And then the height is 375 micron vertical height of the vertical channel, and then this is the height of the base. So WB, which is the thickness of the solid one, is 25 micron. WA, which is full width right here, is 45 micron. So these are all microscale geometry, and hence the Reynolds number is very low, and these are all laminar flow because of low Reynolds number. And here it shows that we fill this up with large number of grids. It's very easy to model these things. So easy to input 428,000. We begin with smaller number of grids because computation is less. Then we repeat that until we find converged results. Results is not changing anymore. So we say that that highest number is our optimum number. We don't have to go anymore. So here are different parametric run we did. We ran it for pure liquid, e.g., then 1% copper, 2% copper, 3%, similar silicon dioxide, and similar aluminum dioxide also. And at different Reynolds number, at different fluid will have different Reynolds number because the density viscosity will change, different Reynolds number we find. For liquid, the Reynolds number for the same volumetric flow rate will be higher because the viscosities, viscosity and density are higher for the nanofluid. So viscosity comes in the bottom, so nanofluid will give lower Reynolds number, and pure liquid will give slightly higher Reynolds number of the same volumetric flow rate. This is the average temperature of our base, so we calculate the average temperature of the base. This is the heat transfer coefficient we calculate within the channel, and we see right our theory. Theory predicts that when you use pure liquid, average heat transfer coefficient here is 36,900. And these are realistic number. We hand calculate also, we get realistic number in the rectangular channel. With nanoliquid, the theory says because we are using very pure, well-purified thermal conductivity equations, these are much higher. 41,800 is the heat transfer coefficient. So theory says that the heat transfer coefficient of pure liquid and nanoliquid will be much different. Nanoliquid will be always better. Nanoliquid gives higher pressure loss because it's more viscous. We get more average pressure in the channel, and low pressure we get for the pure liquid. Similar kind of thing we find here. Here the heat transfer coefficient, exactly similar kind of results we find. And one thing good also we find is that if you use pure liquid, then the base can only be cooled up to 318. If we use nanoliquid, it could be cooled to 316, little bit cooler. So it is showing, it's not yet perfect, it's showing that when we circulate pure liquid, that using them now, the base runs a little bit hotter. When we introduce nanoliquid, the base runs a little bit cooler, so the chips will remain a little bit cooler. So theoretically, it is always predicting that we'll get improved results. Then we plotted the results. This is axial distance, this is entrance of the microchannel, end of the microchannel, axial position and heat transfer coefficient. In the entrance region, heat transfer coefficient is always high, as normal theoretic predicts. And at high Reynolds number, we get high value. All these orange color on the top, at high Reynolds number, as our theory predicts, we'll always get higher heat transfer coefficient. At low Reynolds number, these blue ones will get low heat transfer coefficient. And as the flow proceeds through the microchannel, it becomes fully developed and the heat transfer coefficient becomes constant. These are all very traditional heat transfer results, which proves that the calculated results are correct. Similar average base temperature our goal is to cool that base on which chips are mounted. So average base temperature is very low with the nano liquid. When we have 60% copper, 3%, 60% Eg and 3% copper oxide nano liquid, the base temperature is much cooler. When you have the pure liquid, which is right here on the top, and those pure liquid is 60% Eg, this pure liquid, the base temperature is much hotter. So theoretically, we did this thing, same thing with the resistance value. The lower part shows that the nano liquid gives low thermal resistance, so the heat goes from the heat flux of the chips very quickly into the liquid. So this is our conclusion. We found that being in doubt after experiment, we wanted to again go back to our involved computation. Initially, we used to do some analytical calculation to prove superiority, but with very involved CFD modeling, we found that still the prediction is that nanofluid has potential, but the difficulty is that we haven't been able to reach the stage where we can find very good quality nanofluid and use it. So the 3% copper oxide exhibited superior heat transfer coefficient compared to base fluid. Reynolds number, practical, realistic Reynolds number 300, and 3% copper oxide produced low thermal resistance. All nanofluids lower the average base temperature of the domain, so they maintain the chips a little bit cooler, and the pressure loss always is higher for any kind of nanoliquid. So we got higher pumping power. So this is our final conclusion. Computational work supports the notion that nanofluids may provide superior performance in cooling applications as well as heating applications. But it is very challenging converting the favorable empirical transport property data, the equation of thermal conductivity, specific heat that we are putting into model. It is very difficult to replicate that, convert that to real world to get practical results. And formulating and storing nanofluids are becoming very critical because agglomerating, we have to develop very resistant nanofluid which will be stable. Environmental issues are there which should be considered for nanoparticles when the nanofluid or nanoparticles are disposed of after they are used, the potential to be persistent environmental contaminants. So those problems all remain, and I acknowledge my gratitude to my former PhD student, Dr. Roy Strandberg. This is his dissertation work, and also University of Alaska Fairbanks for providing all the mechanical experiment equipments and to all the financial funding they have provided. Thank you very much for your patience, and I'll be very happy to answer any questions you may have.
I invite questions from the participants.
Can I ask a question, please?
Yes, sir, please.
Okay, Doctor, I am Sanat Kumar from India. My questions may be a little bit blind, but nevertheless, I have two questions. One, you have tried with aluminum-based nanofluid. Have you tried silver-based or graphite-based? Am I visible? Am I audible?
Yes.
Have you tried silver-based or graphite-based nanofluid? Question one. Question two is, in metals at least, heat transfer coefficient, heat transfer coefficient varies with temperature. Higher the temperature, lower the heat transfer coefficient sometimes. For example, uranium oxide is like that. Did you find a similar case in the nanofluid also? These are two questions, maybe very blind, but please try. Thank you.
Okay. We have not tried silver nanoparticles, and we haven't tried the graphite particles yet. And I think the primary reason is that most of the people who are working in nanofluids area, they are looking for the metals which are very inexpensive and which has high thermal conductivity. So the two metals which have been selected are copper and aluminum. They are relatively cheap and their thermal conductivity is very high. So most of the experiments have been done by the researchers in these two nanoparticles.
Silver and
We have
graphite will give you higher values. Silver and graphite have got better thermal conductivity. That they may give you better values.
Yes, and silver has higher thermal conductivity. Gold has higher thermal conductivity. Platinum has superior thermal conductivity. But people think that in the ordinary household heating coils, which we produce in millions, we won't be able to use them. We are also trying to use this in automotive radiators. We have done some research, and we are thinking that we won't be able to use these expensive nanoparticles. So we are doing research on practical, realistic particles which will make, and these are very inexpensive. And eventually, when these technologies are perfected, we'll use them in massive scales in tons, and it will be very cheap. People can afford it. So that's the reason why we haven't done other nanofluids. And probably I have seen 80 or 90% of the universities and research labs, they focus on this. Sometimes they also do some titanium nanofluid, zinc nanofluid, but those metals are very cheap, very inexpensive. And I'm sorry, what was the second question you had?
Thermal conductivity variation with temperature. You know, yes. Metals have got thermal conductivity quite varying with temperature. Higher the temperature, lower the conductivity happens. So did you find a similar problem in the nanofluid also?
We have good hope. The good hope is that the aluminum and copper that we have found, we have selected, as the temperature increases, its thermal conductivity steadily increases within a practical range. So, and we have found from all our analysis that if we'll use nanofluids at a higher temperature, high temperature nanofluid, it will perform even better. All our theory and everything says that. So right now, we are testing it within the temperature range of automotive radiators and household heaters and microchannel chip coolers. And here we need not too hot temperature, but as we prove this technology, someday we'll go to much high temperature heat exchangers in big industries. And there at high temperature, our hope is that nanofluid will also function better because our calculation is leading to that direction. That at high temperature, these nanofluids will perform, this H will be given the same Reynolds number, the heat transfer coefficient will be better. It holds promise.
Thank you, sir. Thank you. Thank you very much.
You're welcome.
Okay. Thank you.
I invite any other question. So this is the end of the session. I would like to extend my vote of thanks. Honorable Vice Chancellor, Professor B. Debendra sir, Honorable Professor Debendra, Chairman, IIM Bhubaneswar Chapter, Chairman Advisory Board, SK University, Professor Sri Pankaj sir. Yes, Honorable Damodar Acharya sir is there with us. I would like if sir wants to speak something. Unmute, sir. Kindly unmute, sir. Yes.
Hello,
Yes, sir. You are audible, sir.
am I audible?
Yes, sir.
Yes, yes, sir. You are audible, sir.
Okay. So, thank you, Professor Das, for such a beautiful talk. I couldn't attend all through, but in between I was coming and going. But what is more interesting is the way that you predicted your results theoretically, and that the way that you try to validate it through experimental things, and the learning that you got from actually those experimental things, and again you modified. This is something very interesting, and everybody should really try to do that. But many a times what happens in most engineering things, we end with only the theoretical calculations, and we predict something with simulation and things of that type, but we never actually go into this depth. This is something is very, very interesting, and I'm really not in Bhubaneswar, so therefore I missed the whole of it. But definitely, it was a great thing, and such a short notice you could do it. I'm really very, very thankful to you for this one.
Thank you.
So now actually you can propose your formal vote of thanks and whatever that.
Thanks. Honorable Vice Chancellor, sir. Professor P.K. Nanda, sir. Honorable Professor Damodar Acharya, sir. Chairman and Bhubaneswar Chapter. Chairman Advisory Board, SO University. Professor Shripad Karmakar, Director, IIT Bhubaneswar. Dr. Ramanuj Narayan, Director, CSIR MMT. Esteemed Speaker, Professor Debendra, sir, and distinguished esteemed participants and my distinguished professors from the university and nature subsection at across IMD. I, Dr. Renu Sharma, on behalf of Shiksha Anusandan deemed to be university, extend heartfelt gratitude on behalf of CSIR, MMT Bhubaneswar, IIT Bhubaneswar, and IEEE Bhubaneswar subsection to Professor Debendra sir from the University of Alaska, Fairbanks, for enlightening us with his profound insight on nanofluid research. His expertise and engaging lecture have broadened our understanding of this cutting-edge technology. Thank you, Professor, for valuable time and the knowledge you shared, inspiring us to delve deeper into the fascinating world of nanofluids research. Thank you, sir, for your valuable contribution to our academic community. Thank you so much. Thanks to all of you for joining this distinguished lecture, that is 30th distinguished lecture of the series. Thank you so much. Namaste. I would like Honorable Vice Chancellor to felicitate our distinguished speaker of the day.
It's my pleasure to felicitate very distinguished Professor Das. Sir, sir. None of us see the reason. Sir, boss. Sir, pleasure, sir. On behalf of actually Professor Damodar Acharya, I am presenting. Sir would have presented here. That was nice. Thank you, sir. Thank you.
বিবেককে পঠিয়ে দেওয়া কতবার ইমেল অ্যাড্রেসে কিছু ফটো মেলে ঠিক পাঠিয়ে দেওয়া
With this, we come to the end of this session, lecture series of this 30th lecture of INE. I thank everybody to join. I thank our esteemed chairman of the advisory board, the INE chairman, Bhubaneswar chapter chairman, Mr. Damodar, to join. Also, in spite of the connection issue at his place. So I thank again our speaker who is with us at Bhubaneswar in our university itself and in the room and shared his expertise with all of us. Thank you, sir. Thank you, everybody. I think we end this session.
Thank you.
Thank you.